And we're back, guys. I'm going to talk about, like I said, adiabatic processes or adiabatic curves and the Carnot cycle. So I've already drawn this axis because on the other video. So an adiabat is a process with constant heat. So heat isn't flowing. Is a better way of saying it, because heat is when we say heat in physics, we don't mean like any specific type of energy. We mean a method of energy transfer. So maybe a better way of saying this is no heat exchange. It's probably a better way. So those are going to look kind of like isothermal curves, but they're going to be really steep. So if I wanted to do a process like this, same thing, I would probably have to do it kind of, so it's a little bit curved. And this one will be probably, might fit it on there, kind of. You get the idea. I should have better axes, but so we could have a process that looked like, a cycle that looks like that. Oop, that way. And so you're still doing work because there's area under this curve. So energy is leaving the gas by work. Energy is entering the gas by work. But there's no heat flow on those sides. And on these other sides, since these are still isocores, so they're still have no change in volume, we have no work we're doing, so I know that energy is entering through heat and energy is leaving through heat. So that one's a really, really easy process because I know that there's only certain types of energy exchange in those different parts of the cycle. So let's talk quickly about the Carnot cycle. Now the Carnot cycle is this special, magical, theoretical cycle, so it doesn't actually exist, which is the most efficient cycle you can possibly have in theory. But of course we can't actually get there because it requires infinite time and no friction and all kinds of things. So let's look at that. And Carnot, I believe, has a French origin. So it looks like Carnot, but it's Carnot because French. So on the Carnot cycle, once again, I'm not going to worry about numbers on this because, well, I don't want to calculate them. So this, you're going to have two isotherms connected by adiabats. So we go A, B, C, D. So this one here is isothermal, so you have constant temperature. And this one here and this one here are adiabatic, meaning no heat's exchanged. So this is the most efficient gas cycle you can have in theory. Now, but to have a true isothermal curve, since we do have heat exchange through here, we are still, having energy leave through work and having energy enter through heat. Right? So if I'm having energy enter and leave, it's really, really hard to do this perfectly to get it isothermal. So in theory, actually, since that heat's coming in and you want it to be all uniform, this process here would require an infinite time for it to actually be isothermal. And the heat is also same direction here. So heat. You'll also notice that on these processes, it's usually entering on the top if I'm going clockwise and leaving on the bottom if I'm going clockwise. And the work is doing the opposite. And on these processes, we still have work happening, right? Because they're adiabatic. So there's still area under this. It's like pretty small, but there's still area under it. So because we're moving to the right, I would say the gas is doing work, right? Our volume's increasing, even though pressure is decreasing. So say hi to my dog. It's Cicero. He's adorable. And this one, work is being done on the gas because the volume is decreasing. But there's no heat exchange on these sides. Now to have a process, I'm just writing down isothermals require an infinite amount of time. To have a process that you exchange no heat in, but your temperature is different in these 2 points, you actually have to have it happen instantaneously. So we can approximate this, but we can never actually do it. So let me catch up my notes. I'll pause it and write these down so you don't have to sit here and watch me. Yeah, so both of these processes never actually occur in real life. We just can approximate them. So to approximate an adiabat, which has to be instantaneous, we just do it really fast. So you can think about like in a car. Well, when you inject the fuel, you light the fuel, it explodes. I did air quotes there, but you can't see them. Explodes. And the piston rises. We can say there's parts of that process that are adiabatic. But if you still put your hand on the hood of a car, it is definitely energy leaving in the form of heat, right? So it's not truly adiabatic. But it can be close enough and to make the math sort of work. All right, so how do we define efficiency? Well, we actually are going to use the symbol eta. This is a Greek letter eta. It looks kind of like an N with a curly tail down here, a cursive N with a curly tail. And that we're going to define that as the work you get out over the work you put in. Because if you're getting out as much work as you put in, or the energy you put in, I guess is a better way of doing this. Let's do this. Energy you get out over energy you put in. Now, most of the time, the energy you're getting out for it to be useful is work. But you can put in heat, because this energy is going in, that had to come from somewhere, so that has to factor into your efficiency. So, sorry, I had to pause to answer some student questions. So the energy you get out, so this work that you're putting in here, those cancel out. So the energy you get out is just going to be work in this section. And the energy you put in, we can actually just say that's heat. So this is specifically the heat flowing in here, because this isn't useful to us. This isn't what we're putting input. So we're going to say Q hot. So now the work that we're doing, because like I said, these guys cancel out, is going to be the work you get out here minus the work you put in here. So that's going to be, and those are both equal to those heats, right? So it's going to be, I guess I should say the net work. So I should say work hot minus work cold over Q hot. And so this is going to be And so the work I'm putting in here is the same as the heat. The work I'm getting out here is the same as the heat I'm putting in here. So I'm going to rewrite that in terms of heat. So everything's in terms of heat. Q hot minus Q cold over Q hot, which I can then simplify this expression by factoring, by separating these. So I can get Q hot. You can just skip to the answer if you guys want, but Q hot minus Q cold over Q hot. So that's going to give us an answer that looks because this is 1, so we get 1 minus Q cold over Q hot. Right? And there's one more thing I can do, because I know that the heat, the change in heat, is proportional, or not the change, just the heat, is proportional to the change in temperature. And since if I have the same mass for both the cold and the hot, it's just going to be the ratio of the temperature. So, and since I know the temperature is the same all along this line, and the temperature is the same all along this line, because they're both isothermal curves in a Carnot cycle, then I can just do the ratio of the temperatures. So I can say my efficiency is equal to 1 minus the temperature at the cold over the temperature of the hot. And that is the theoretical maximum efficiency you can have for a heat engine. Carnot efficiency is what we'll call that. And you can never be 100% efficient unless you were able to run this to an absolute zero reservoir. But as soon as you put any ounce of energy in a reservoir as absolute zero, it's no longer going to be absolute zero. All right, well, go ahead and stop this one. And I think in the next video, we're going to talk about refrigerators, guys. See you later.